Welcome to the Crazy Hat Chemist. So today we're doing another video on thermochemistry, so let's get moving. BAM! So today we're going to be talking about a generic heating curve. So on the y-axis here is temperature, on the x-axis is constant heat that is applied to the system throughout this here. So take a look at that graph. It is an idealized graph, and notice that it's a sharp delineation here. So what defines the graph are essentially two sections of it. The first section is right here, and this is the MP, which is standing for the melting point. The melting point, the freezing point are one in the same. The next point is the boiling point. The boiling point is the second point that defines this graph. So if you figure out what the melting point is, what the boiling point is, and you write down those values along the y-axis, then you're going to be set for the rest of it. So let's figure out more details about this graph. So, along these sloped sections here, you will see solid, liquid, gas. Hopefully that makes sense, the three states of matter that we're talking about in chemistry. Now, in between these here are two flat sections. So the lowest flat section is the interconversion between the solid state and the liquid state. And the top flat section is the interconversion between the liquid state and the gaseous state. Now, depending on which direction you're going, if you're going from the bottom of this graph in the lower left-hand corner all the way up, that is solid, liquid, gas, then you're going from the solid and then you're melting it to the liquid and then you're boiling it to the gas. If you're doing it the other direction, starting out with the gas and then you're cooling it down and going through condensation and then solidification and then finally a solid. Okay, so a little bit more about this graph. This solid section here, which I'm going to call step 1 in just a little bit, but this solid section is Q equals mc delta T. And that C is the specific heat capacity for ice. And I'm going to talk about a generic curve for water here specifically. But it is the solid form. Generally, you're going to have these for water, H2O. Okay, the next section here is going to be the Q equals mc delta T, but this C, specific heat, is the specific heat for the liquid, that is water. That is the 4.184 joules per gram degree Celsius that you're familiar with. Okay, the next sloped section is Q equals mc delta T. That C is the specific heat capacity for the gaseous state of H2O. Okay, now, depending on what your instructor professor gives you, okay, the specific heat capacity might be the same. If they don't give you other values, you might be able to use the same value and get a really close approximation. So let's discuss the other two sections of this graph. So that first lowest flat section of that graph is going to be Q equals mc, and the C is going to be the heat of fusion. There is no change in temperature. Notice that this section of the graph is actually horizontal, and since it is horizontal, there is no temperature change. This is occurring at the melting point. Okay, so then the next flat section as we move on up is Q equals mc and the heat of vaporization. Again, this is a flat section of the graph, and there is no temperature change. So notice if you go all the way to the boiling point, there is actually no temperature change here. That's why there's no delta T in either of these. Now we're going to delineate these as steps. This is step 1, step 2, step 3, step 4, and step 5. So what you're going to have to do on these problems is do a rough graph of it, figuring out where your melting point is, figuring out where your boiling point is to define the graph. Then from the problem, you're going to write down the lowest temperature, put a dot there, the highest temperature, put a dot there, and you're going to connect the dots. And you're going to do whatever is necessary mathematically to connect those dots. You might have to do just steps 1 and 2. You might have to do just step 3. You might have to do all 5 steps. Okay? So here is some information, some data for just water. That is, if you look at the bottom section here, I'm starting off the bottom, not at the top here, because it goes with the graph. That's why I'm starting off with the bottom. Step 1 is a specific heat capacity for ice, and the CP for ice is 37.8 joules per mole Kelvin. Again, you can change these kelvins into degrees Celsius, and that's perfectly fine because the interval for degrees Celsius and Kelvin is the same. Step 2 is the heat of fusion, that's 6.01 kilojoules per mole. Notice that there's no temperature units in this because this is a flat section of the graph and there is no temperature change. Step 3 is a specific heat capacity for water, and we know that as 4.184 joules per gram degree Celsius, or Kelvin in this case. This is also the molar heat capacity, and that's 75.4 joules per mole Kelvin. Notice that that's in moles. Okay, step 4 is the heat of vaporization, and that's 40.79 kilojoules per mole. Step 5 is a specific heat capacity for steam, and that's 36.5 joules per mole Kelvin. Okay, I want you to notice something here, that there is such a large number for the heat of vaporization. Okay, that lets you know that water in the steam can really burn you quite severely because there's a tremendous amount of heat contained within that. Okay, what I want you to do is review this here and review the graph, review the math equations that you're using on the graph, review the states of matter that are on this graph and what defines the graph as the melting and boiling points, respectively. Okay, that was another great video in thermochemistry, and I am all bare about that. Give me a thumbs up if you like that video. Please subscribe to my YouTube channel. I greatly appreciate that. And have a delightful day until next time when we talk about more chemistry. Bye now.